Okay, so just for Brody who's not here, worksheet 3.6, we're done with the notes. We've covered enough. The worksheet I'll make it due Thursday instead of tomorrow. Thursday during 7th period, if you want to come, Landon and Devin are going to be doing AP review, and I think they're going to be doing optimization, right? And then our math club meeting we postponed, not because Zachariah wasn't ready. Oh, he's ready. But there's a scholarship meeting during advisory tomorrow. Okay, sketch F prime from the graph of F below. So there's the graph of F. First of all, when you're talking about F prime, F double prime, don't use pronouns, whether you're talking to me or someone else, or especially if you're writing it on a test, because it's just too vague. There's too many nouns that we can refer to. So don't also just say the slopes. Okay, don't do that either. And also remember that you always want to justify by talking about a sign or a sign change. So when you start throwing around the words like increasing or decreasing, like, oh, it's increasing at a decreasing rate, or the slopes are increasing. Now it's like, wait, the slopes of what, right? And some people misspeak. F is increasing when F's slopes are positive, right? So that would mean that F prime has positive Y values, but you don't want to say that F prime's increasing, because that's talking about the second derivative, okay? So we have the graph of the Y values at certain values of X, and all we want to do is analyze what the slopes are. What are the slopes of this blue graph at different values of X? And we want to plot a Y value that will represent a hypothetical slope of the graph at that same value of X. Okay, you don't need to be looking at increasing at an increasing rate or increasing at a decreasing rate. You don't need to be looking at any of that for the derivative. Okay, the first thing you want to do though is look to see where this function has horizontal tangent lines. Okay, because that's really the only place where you know the true value of the derivative, and that's going to be at your horizontal tangent line. So I'll choose purple. So right there, whatever that X value is on F, I know that there's a horizontal tangent line to F, so the derivative F prime is going to have a 0 there. There's another one here. There's another one here where F bounces. Okay, so those are my three horizontal tangent lines. Now there is another critical value, yes, because F prime has a local max and a cusp right here, whatever that X value is. Now, I don't know if the slopes on either side are going vertical or if they're just coming in at a sharp turn, okay? So I'm just gonna assume, since I didn't draw them vertically, that it's not vertical. If you're only given a graph, how are you gonna know if it's going vertical or not? It'll say so in the description, okay? It'll actually say F has a vertical tangent line at whatever. And they're like, oh, it goes so steep there, it's vertical, okay? So now all we got to do is figure out, okay, in between these x-intercepts in purple of F prime, what are the slopes of F? First of all, look for the sign. Are the slopes positive or negative? Then you want to know, what are the slopes doing, okay? Are they getting bigger or smaller from left to right? So you can always come up with hypothetical values, all right? So if you look immediately to the left of the leftmost purple dot, the slope there is like positive 1/2. Yeah. So I'm going to go ahead and just plot a small positive Y value that represents possibly a 1/2. As I continue further to the left, right, now my slope is like a positive 1. So it's a little bit bigger. So right there. If I keep going to the left, now my slope there is about a positive 3. So now it's a bigger value. If I keep doing that far over here to the left, now my slope is like positive 100. Well, at that X value, 100 is going to be up here. Okay. You see what we're doing? It feels like algebra 1, except we're looking at slopes and plotting their possible value. If you then continue the trend, you get that. All right. So far, so good. Now you look between the next two x-intercepts and you can clearly tell that the blue graph is going downhill. F is decreasing. If F is decreasing on an interval monotonically, right, we know that its derivative is going to be negative. So I'm going to sketch my values below the x-axis from purple to purple dot. If you go immediately to the right, your slopes are now like a -1/2. So that's going to be like about right there. Continue going. Now it's like a -1. So at that X value, it's now a -1. Well, where is the graph the steepest in the negative direction? Oh, I don't really know. It doesn't tell you, right? So if we eyeball it, I'm just going to say right about there. Okay. If that's going to be where my graph is the steepest in the negative direction, what's a hypothetical value? Maybe -1.5. So at that X value, I'm just going to draw a value that is low. And then what happens now on the other side? Now the slopes of F start increasing, right? They become flatter. Their magnitude is approaching 0, but the values are increasing because they're becoming less negative. So that's going to make them come back up. Boom. And now, again, you could just kind of make it smooth. This looks like a polynomial. It not necessarily is, but if you have a polynomial curve-ish, nice and smooth, and you're trying to sketch its derivative, just make sure it's nice and smooth. So what's important then is that on the blue graph of F, the point where the slopes are the steepest ends up being a what point of F? It's an inflection value, right? This inflection value of F, inflection value, and the value is the X location, right? The inflection value of F ends up being the local, in this case, it's the local minimum location of F prime, okay? Now, how low do we go? We don't know. Yours might be lower than mine, might be a little bit bigger. That's all qualitative, right? Subjective, but the X should correspond. All right, we keep the idea going. Now, what's happening on the next interval? Well, there's a cusp, right? Before I get to the next purple X-intercept. So what are the slopes doing? There's 0, and now it's like a +1/2, +1. So let me just go ahead and say that it's a +1/2. And then over here, it's like a +1. And now what is a hypothetical slope right there as I reach the cusp? Oh, 4 billion, right? Or it could be 4 or 400,000. I don't know, but wherever that X value is, I'm going to put like a little dot, okay? And it's going to increase up to whatever that point is, okay? Now, because the derivative there does not exist, I'm going to put an open circle, okay? And we'll talk about what happened if it did go vertical there. Now, immediately to the left-hand side, it kind of looks symmetrical, doesn't it? Through the vertical line that would come down the middle of the cusp. So immediately to the left-hand side, if I'm calling immediately to the left 4 billion, then immediately to the right, it might be -4 billion-ish. Well, that's going to be at somewhere right there. Now, again, I'm going to put an open circle. And as I go to the right, the steepness is decreasing, right? The steepness is decreasing on the blue graph, but the slopes again are increasing because they're becoming less negative. So -4 billion, -4, -1, -0.5, approaching 0. So how's it going to approach 0? Kind of curving like that. And now as I go to the right, I'm kind of home free. I have 0, +0.5, +1, +2. So then, man, I didn't give myself, I went too low. So notice I'm going to modify it. I was going to go off of my screen there. So I'll just kind of do this. And we'll keep it going. I'll put arrows at the end. Once I'm done, I'll call that F double prime. Okay, something to that effect. Now compare it to yours. Does it look similar? Hopefully. Now, what if it did say that? Yeah, go ahead, quick.
So,
Not quick, but you know, thoroughly.
so does it matter like if we drew like this versus like this normal curve?
Oh, if you kind of wiggled as you went through the X,
Yeah.
Why does it not wiggle? I thought it would wiggle.
you thought it would wiggle going through there? Well, when you wiggle going through there, again, think about like a parabola, like a curve. It's going to have a derivative that's a curve. Like, did you have it wiggle the other way? Like, You had it doing like this and then like that.
Yes.
Okay. Well, if you look at that now, look at your Y values in purple. They're that wouldn't necessarily be wrong. Okay. That's getting down to having to really analyze how the slopes are changing on a much smaller interval. Okay. So you wouldn't necessarily lose points for that, but it actually doesn't quite do that. Okay. You can look at the Y values. They're right. Without getting, I don't want to confuse anybody as we're trying to clear this up. Okay. But again, if you wanted to go back like this, look at the Y values in purple. In the very few X values past the open circle, your Y values are approaching the X axis very quickly. Okay. So if you look at that, that means your slopes are increasing very quickly. Your slopes are not changing very quickly here, are they?
Oh, no.
Your slopes are actually changing more quickly as we get closer to the curve, right? Because think of most of your energy is in coming down, like if you know what vectors are. And then as you get past a certain point, now they're changing more rapidly, your slopes. So your Y values should reflect that. You have your Y values going to the X axis very quickly, but that would imply the slopes are changing faster. And then over here, as we get closer to the purple dot at the X axis, you have your Y values changing not as quickly. Where in reality, if you drew a tangent line, as you get closer to the bottom now, the slopes are changing quickly. So it's, again, if you understand that, that's great. It doesn't quite do that, okay? So don't get too curvy, right? Don't get too curvy. Just kind of connect the dots, all right? Now there is F double prime. If it had said that the function had a vertical tangent at the cusp, then the only thing that's different is instead of putting open circles here and here, there would be a vertical asymptote, and now it would curve up towards infinity, and now here it would curve down like that. Yeah. Okay. There you go. Yeah, and I labeled it with 2 primes. There you go. Think that would be real confusing, right? There you go. Okay, boom. And that's it. That's it. That's all I'm going to do for today with that. So hopefully that helps so far. We'll just compartmentalize that. That's going from F to F prime, or from F prime to F double prime. We're sketching the derivative. Yes.
So if we did like the vertical line thingy and it didn't tell us that,
You probably wouldn't lose points again. No. But remember, you can have a cusp without it going vertical, right? A vertical cusp would look more like that, whereas you can have something that looks like that. So just because you have a cusp doesn't mean that the slopes are going vertical. So just realize, if there's no equation, you would be told if there's ever a vertical tangent line. All right, so that takes care of that. We'll do like one a day for a while. All right, now what I want you to do is download 3.7, linearization and differentials. All right, and you got to get it from Corpy's World, because I haven't put it on Canvas yet. So this will kind of give us a nice break between the 2 word problem sections. Linearization. Okay, so what is linearization? Linearization is basically when you use a tangent line to approximate a curve. You're linearizing it. Now, if the function is differentiable, then we had this idea earlier in the year called local linearity, right? A function is differentiable at x equals c if it's locally linear at x equals c, and vice versa. They're interchangeable, okay? Now, locally linear, I think we did the activity where we took a curve and we zoomed in on it repeatedly with the calculator. And after you zoom in on a point that's differentiable, you don't see the curve as much every time you zoom in. In fact, if you zoomed in continually, you wouldn't see the curve at all. It would look just like a line, and not any old line. It would look like the tangent line, right? Zoom in at any point on a differentiable function at that point, and you'll see soon enough the tangent line. Okay, so the idea is, back in the day before calculators, and even still to this day with programs, right? A tangent line can be used to approximate a curve in the neighborhood of the point of tangency. Okay, so for instance, if you look at the graph of y equals the cube root of x, okay, look way out here at 64. All right, way out here at 64, we have the ordered pair 64 comma what? What's the cube root of 64? 4. Okay, so at the point 64, 4, we can draw a tangent line. All right, now if you draw the tangent line, you can kind of see that it's really hard to differentiate between the tangent line and the curve itself for quite a while until they start to separate. So if you wanted to approximate what the cube root of a number is in the vicinity of a known perfect cube like 64, you might just be able to use the equation of the line to get that value rather than the equation of the cube root of x, because it's easier to obtain. And sure, they're not going to be the same. They're only the same at x equals 64, but you're going to be so close that maybe some people won't even know the difference. Okay, so that's the idea. This right here, the point of tangency, we call now we call it the center of the approximation. And we use x equals c for that. This is going to kind of carry over when we study Taylor polynomials later in the year. Okay, but right now we're sticking with a line. So notice that at the point of tangency, at the center of approximation, the equation of the line and the equation of the cube root of x have the exact same value, right? Remember, at any point, two functions and its tangent lines share the y value and the slope value. But if I go left and right by a certain amount, call it plus r and minus r, where r is the radius, think of it as a radius, I can go left and right of my center of approximation by a certain amount and get pretty good results if I'm going to be using the line to approximate the curve, right? Now, depending on the curve itself, this one is pretty flat out there. That radius might be bigger or smaller, okay? So notice that after a while, though, it's not going to be any good. But even look at this, way out here, like at 110. If I was really interested in this value here, that is, if I wanted the cube root of 110, does anyone know off the top of your head what the cube root of 110 is? No, I don't either. I could use this value here. This is the tangent line value at x equals 110. Now, again, they're not going to be the same, but look how small the error is. And of course, 110 is miles away from 64, really. So I could, with confidence, use the tangent line equation, which is much easier to compute for any value that's between 64 and 110, and get a better result much more easily. For example, I should say, let's try 70. Let me show you how this is useful. We're going to approximate the cube root of 70 by using the tangent line, okay? Now, you're going to be given the center of approximation. You don't have to find one, but let's say you're at a math club meeting and you're just challenging people in the audience there to come up with a pretty good example of the cube root of 70. You would want to find the closest perfect cube to 70 that you could. So what would the perfect cube closest to 70 be? Well, 3 cubed is 27. That's not too far away. Okay, that would give us here. But hey, 4 cubed is 64, and that's closer to 70, right? So we would choose 64 as our center of approximation. And now all we got to do is write the equation of the tangent line at 64. And once I have the equation of that line, I can plug in any x value I want, like I'm back in Algebra 1 class, yes? So really what we're going to be doing in this section is writing equations of tangent lines, where we're going to be using them. We've been writing equations of tangent lines pretty much all year. So what do we need for the equation of a tangent line? In Taylor form, by the way, some people were missing this on the memorization quiz. Here it is, all right? This is Taylor form. For equation of a tangent line, we need a slope and a point, we need a slope and a point, we need a slope and a point. So we're going to let our center of approximation be x equals 64 because it's the closest perfect cube to 70. All right. So that's essentially our x value. Let's go ahead and find the y value. All right. If I let my function, again, be y equals, then y of 64 is the cube root of 64, which we already found to be 4. Yes. So now I have the point 64 comma 4. All I need is the slope now at the point. Slope at a point, well, that's the derivative, yes? So if y equals the cube root of x, that's the same as x to the 1/3. Let's go ahead and take the derivative. Y prime is 1/3 x to the negative 2/3. Calculus. Now let's simplify that because we're going to use it. So that's 1/3 cube root of x squared. Now I'll plug in my x value again. So y prime of 64 is 1/3 the cube root of 64 squared. Now remember, cube rooting and squaring have the same priority level. So let's go ahead and take the cube root first and then square it. What's the cube root of 64? 4. 4 squared is 16. And if I multiply those out, I get 1/48. So not surprisingly, it's a pretty small number. I could tell that the graph is pretty flat out there. So here's the equation of a tangent line, right? So the equation of the tangent line is y equals the y value, which is 4, plus the slope 1/48 times x minus the x value. And that's where we stopped before today, right? By the way, what would the equation of the normal line be at the same point, 64 comma 4? Y equals 4 minus 48. Good, the opposite reciprocal, okay? So here's what we're going to do next. Now that we have the equation of the tangent line, whoopee, we're going to rename it because we're going to use it. And I like to use this letter, L. Yeah, L. And I like to use the capital script letter L, cursive L, because it's fun to make. If you've ever seen old episodes of Laverne and Shirley, Laverne had that L on every sweater she wore. Okay. Now this is x to the first power. It's the simplest polynomial out there that we can use. Much easier than computing the cube root of a number. All right. So let's go ahead and use this then. We're going to say then that the cube root of 70 now, 70 being really only 6 units away from our center, is approximated by L of 70. Right? And that's where you're going to use the squiggles because it's indicating what we're doing. We're going to find the actual value by approximating it with L of 70. And L of 70, by the way, is actually equal to 4 plus 1/48 times 70 minus 64. So notice we don't even want to put it in a different form. If you leave it in Taylor form, then when you're choosing a value of x that's near the center, that number minus 64 is going to be easy to calculate, right? Now let's just simplify this without a calculator, right? 4 plus, let's see, 70 minus 64, that's 6. So that's 6/48, which simplifies to 1/8. And now, You may not know what 1/8 is as a decimal, but you could get the decimal approximation. Do you know what it is, Mason? 0.125. So this is 4.125. So there you go. The cube root of 70 is about 4.125. That's better than saying it's about 4 point something. You could probably get 4 point something pretty easily because it falls between 4 cubed, which is 64, and 5 cubed, which is 125. You might be even able to say that it's going to be closer to 4 than it is to 5, because 70, bless you, is closer to 64 than it is to 125. But 0.125, I mean, that's 3 decimals, right? Now, of course, that's not the exact answer, but I do know that the exact answer is whatter than that, bigger or smaller, or do I know? It is small. How do you know it's smaller than that, actually? Ah, there you go, right? The tangent line, as you can see from the graph, is above the curve, right? And that's because the graph of the cube root of x is concave down between the center and our value of x that we're approximating at. It has to do with concavity, okay? So you might be asked to determine if that's an over or an under approximation. So let's go ahead and say this. The cube root of 70, or how about this? We'll write this sentence. L of 70 over approximates the cube root of 70. And the reason would be, comma, because you don't want to just say because the tangent line lies above the curve. That would not be incorrect. But again, it has to do with the curvature, the concavity. So you're going to say because the cube root of x, or y equals the cube root of x, is concave down. And now you can't just say at the point of tangency, because we know the curvature can change, you know, between the point of tangency and the value we're using. So you're going to want to include the whole interval. So you're going to say concave down on the interval from the center, which is 64, to the x value we're computing. All right. Now we knew that from the graph. If we didn't know it from the graph, would we be able to determine that another way? How? By finding the second derivative. Let's see what that would look like. Let's say, ooh, I don't know if it's an over an approximation. I don't recognize the curve. Here's our first derivative up here, right? Let's go ahead and just take the second derivative, and I'm going to leave it in ax to the n form. So now when I multiply, I get -2/9 times x to the subtract 1, you get -5/3. If we simplify that, we get -2/9 cube root of x to the 5th. Now notice that is not always negative. The top is a negative, but it will be negative if x is positive, right? Because the cube root of a positive number to the 5th is positive. And notice that that ratio there will be positive when x is negative, yeah? Because then you get the cube root of a negative number to the 5th, which is negative, and a negative over a negative is positive. So all you would have to say is y double prime. Well, you would say the same thing. Y double prime is now greater than 0, or sorry, it's concave down, is less than 0 for x on the interval from 64 to 70. Okay. Don't say for all x greater than 0. That would not be incorrect. But again, you want to speak to what we're doing. We have the center of approximation, and then we have the x value we're approximating at. Now, I approximated to the right of 64, but we could just as easily go to the left, yeah? Yeah, and then you would say from that number, like say we wanted to do it at 60, we would say y double prime is less than 0 for x epsilon 60 to 64. All right, and that's pretty cool. All right, now let's see what it actually is equal to. I'm not going to pull the calculator up here because it's too hard to do on the computer screen, but I have one right here that's not charged. Oh, bummer. How about this one? Oh man, when you stick them in there, they got to be cradled. Oh, there we go. There we go. Oh, they just turned on. All right, so here we go. The cube root of 70. I'm going to type in 70 caret 1 divided by 3rd power. We know it should be a little bit less than 4.125. And get this. You're gonna be in awe. The cube root of 70 is equal to 4.1212853. Notice we're correct to 2 decimal places, right? We're off by less than 4 thousandths just by using a first degree Taylor polynomial called a line, right? That's pretty cool. And of course, if I would have chosen a value that was closer to 64 than 70, like 65, it would be even more accurate, right? Now, I do have the luxury of drifting out further if I wanted to, and I'm going to have a slightly larger error, but because this curve is so flat out there, it's going to be pretty close. Now, if I wanted to approximate the cube root of 126, I could certainly still keep my center of approximation at 64. But in the interest of being accurate, what could I or should I do in that case? If I wanted to approximate the cube root of 126, use 125 as your center of approximation now, because that is the next perfect cube, right? 5 cubed is 125. So you'd have to write another equation of a tangent line, but you're going to be more accurate again. So this idea works kind of indefinitely. That's the idea of tangent line approximation. In economics, when you hear the word marginal, whatever, it could be anything, right? Marginal revenue, marginal profit, marginal utility, right? What marginal does is it basically, you're at this current level. This is your current level of production, call it C. And you are using the tangent line to predict out, in economics, you're predicting out exactly 1 unit further, all right? And you're using the tangent line value to approximate what the actual value is, because you don't necessarily want to like produce that very next unit and then realize, oh crap, my profit dropped by a gazillion dollars, right? So if you can project out 1 unit and the tangent line says, hey, you're going to lose about a gajillion dollars-ish, now you can forecast and say, no, I don't think so. So that's what marginal is in economics. It always goes out 1 unit to the right of your current level, but it uses its tangent line predictability. Okay, so there you go. Now again, that's going to be something that it's not even going to be that complicated. You're going to be kind of told what your center of approximation is. Let's look at example 2 now. Let's estimate the 4th root of 17. Estimate or approximate, kind of the same thing. So we're on squiggle alert. All right. Let's see. Determine if it's an over or under approximation. So I'm trying to approximate the 4th root of 17. We're not given any information other than that. So we get to kind of build our own system. Well, let's call f of x, instead of just plain old y, let's call it the 4th root of x. Now let's pick our center. What is the closest perfect 4th root to 17? 16, right? 16 is only 1 unit away. All right, so let's go ahead and write the equation of a tangent line to the function of the 4th root of x at 16, the center of the approximation, and then we'll evaluate it at 17. So what 2 things do we need for the equation of a tangent line? We need a point and a slope. All we have is an x value. So let's go ahead and find the y value first. It's easier, right? F of 16 then is the 4th root of 16, and we know that to be 2. So for what it's worth, our center of approximation has a coordinate 16, 2. All right, now we need the slope at the point. So f prime, let's write f of x in this different format first, x to the 1/4. F prime now is 1/4 x to the negative 3/4, which if we clean that up is 1/4 times the 4th root of x cubed. All right, now I'll find the slope. So f prime of 16 is going to be 1/4 times the 4th root of 16 cubed. And again, we don't have to cube 16 first. We'll take the 4th root of 16, which is 2, right? And then 2 cubed is 8. So it ends up being 1/32. So very similar to what we did, right? Except it's a 4th root. The graph is pretty flat out there. When the graph is pretty flat, your radius, which is the distance that you can stray from your center and still be reasonably accurate, it's pretty large, okay? Let's go ahead and write the equation of the line then. So L of x, and by the way, if a question just asks you to write the linearization or to find the linearization of a function at an x value, it means the equation of the tangent line, okay?
So is it okay that we don't have a L of x is equal to
Yes, I'm defining it right here. I'm defining what L of x is. Yeah, so L of x is, I'm not even going to call it y. So L of x is the y value, which is 2, plus the slope 1/32 times x minus 16. There is the linearization of f of x. Again, this is called the linearization of f of x at x equals 16. Just the equation of tangent line. We've been doing it already this year. Nothing new, except in what we're fixing to do with it, okay? Now, when you do use it, you do need to communicate what you're doing, and that includes the squiggles, okay? So now, instead of saying the 4th root of 17, since I know it's f of x, you could say f of 17 is approximated by L of 17. And that's why it's nice to give them each their own distinctive name, which equals 2 plus 1/32 times 17 minus 16 is 1. So that's 2 plus 1/32, which you may not know what that is as a decimal, right? It's a 4th of 0.125. So let's just write this one as a fraction. 2 is the same as 64 30-seconds, so 65 30-seconds. 65 30-seconds. Now again, I ask you, is that too big or too small? Too big. Why? The 4th root is concave down. Where? In France? On the entire interval between the center, which is 16, and the x value we're using. So on the interval from 16 to 17. If you know the graph is concave down, go ahead and say that. But a lot of times you're not going to know. So let's just pretend we don't know. We're going to need the second derivative. Okay. So first derivative was 1/4 x to the negative 3/4. Let me rewrite it. F prime is 1/4 x to the negative 3/4. That's the more useful version for the next derivative. So now we'll multiply and we get negative 3/16 x to the negative 7/4, which when we clean that up is negative 3/16, 4th root of x to the 7. And now again, we're taking the 4th root of x to the 7. So unlike the cube root, this one doesn't live for all real numbers, right? We can only take the 4th root of a positive number. But when x is a positive number, anything greater than 0, what's the sign of the derivative? Negative, right? So if you want to go ahead and say right here at this step, this is less than 0 for all x in the interval between 16 and 17. Again, don't just say for all x greater than 0. Make it between your center and the x value you're using. So, and now we'll answer. So L of 17 blank approximates f of 17. And we said it was over or under. Well, let's say, ooh, I know that if the second derivative is negative, it's concave down. F is concave down. You don't have to say anything about concavity, okay? But if you're then like, ooh, I'm not sure if the graph is concave down where the tangent line lives. So just draw a little concave down. We don't know if it's increasing concave down or decreasing concave down, right? Let's just say it's concave down. So draw the entire frown, baby. And then just draw yourself a little tangent line. Boom, there's a tangent line. Boom, there's a tangent line. Boom, there's a tangent line. Where do the tangent lines live in relation to the curve outside of the point of tangency? Above, right? Is that what I, so here's the point of tangency. To the left or right, the purple's above the blue. So if your graph is concave down, we'll say if, and this is kind of a theorem, if your graph is concave down, then tangent lines live above the curve. Good to know, but you can always draw it if you're unsure. And then let's do the other one. If the graph is CC up like a cup, draw your tangent lines now, CC up. Ooh, now you can see that your tangent lines live below. Then the tangent lines live below the curve. So when in doubt, just draw it out. All right. So yes, now we'll come up here and say, okay, my second derivative is negative. So it's concave down. Again, if you want to draw the guy's eyes, right? Here he is smiling. And you can see, oh, the line is above. So it's going to be an over approximation. Over approximation. Now, by how much does it over approximate? We don't know that. If we knew the amount of the over approximation, we'd be able to know the exact value. Now, it turns out that when we study Taylor polynomials, we're going to be able to find a maximum error. We call it an error bound. We don't know how much bigger it is, but we know it's not going to be more than this amount bigger. So it's going to fall within this interval. Okay, that's kind of cool. That's called Lagrange error bound. It's like the last thing we do at the end of the year. Okay, and there you go. Now, if you're curious what the 4 through 17 is, you could just plug it in. Okay. Now, we'll talk about differentials tomorrow. We did kind of an extended warm up, but that's pretty much what the that's pretty much what linearization is going to be. The only difference is you're going to be given the function, and you're going to be given the center of approximation, and then you're going to be told to use the tangent line to approximate the function. Okay, at a point. So you'll be given all the information. All you got to do is write the equation of the tangent line, use the squiggles, and then possibly, if it asks, determine if it's an over and under approximation based upon the curvature. Okay. And then the only last thing that I'll say here before the bell gets us is the differential. The differential of x and the differential of y. dy is called the differential of y. I think it's over here. Yeah. dy is called the differential of y, and dx is called the differential of x. And you can use those as individual quantities. That's what Leibniz called the ghost of a departed quantity. That's what Leibniz called it. Remember, his method was called the method of infinitesimals. So what I might do next time is just explain kind of what this graph is. And then that's all I'm going to talk about differentials until we get to integration. Okay. So we're pretty much done. I might work one example next time of how you're actually going to be asked to use linearization and not just kind of like the squeeze your own juice. I'll talk about this, and then we're going to move on to related rates. The worksheet for this is very, very short. Right now, concentrate on optimization, and I may assign 1 or 2 problems from the worksheet only for you to do, okay? From this, just to practice the notation. All right. Good day. Good day. All right. Any questions? All right. Have a fantastic lunch and rest of your day.